at the previous lesson we have defined an isomorphism between what we called x tilde n of xy, which is the set of long exact sequences starting at y and ending at x, factor sum equivalence relation, and like we have defined some bijection in this set, and the x that we have defined before is the right functors. So I don't remember if we will need in both directions. What is important is that if we have some long exact sequence, then the corresponding element of x, the map representing element of x from Pn to y can be chosen and in such a way that the following commutative diagram exists. Well, so now we want to understand what happens when we take a sum of two elements here, yes, because here we have sum operation, and here we don't have a sum operation for a while. So let us consider the second element of x and some long exact sequence corresponding to it. Here 0 prime, so on, x1 prime, y, and again we have such maps. So now to understand what long exact sequence corresponds to the sum of f and g, we have to construct some long exact sequence and a map from P, like a map from Pn to y, f plus g, and like fill all these maps in such a way that we again will have a commutative diagram. So how we can do this? First of all, we can take the direct sum of these extensions, yes, these long exact sequences, and we will obtain a long exact sequence. The only problem is that it will start at y plus y and will end with x plus x. But it will be a long exact sequence. To x, yes. Here we have x plus x. Here 0 plus 0 prime minus 1 plus minus 1 prime. Here y plus y. Here we can put the map delta, which is diagonal map. Yes, delta of x is simply xx. Then here we can put the direct sums of these maps. Yes. Well, probably it's not direct sum. It is like when we apply a map, we apply it to one coordinate, and like we apply first map and get the first coordinate. They apply the second map and get the second coordinate. And here, what is here? So here, fg, yes. So the sum of f and g, in some sense. Well, to obtain f plus g, we can compose this map with the map delta. Yes. Which is the map that sends y1, y2 to y1 plus y2. It is called codiagonal map. And then we simply can do not change the part starting from n minus 2. And here we simply make the pullback construction. Yes. We construct pullback of this and these arrows, and then we will get this arrow by not pullback, push out. So and we will get this map by the inverse property of push out, using the conditions that this square has to commute and this composition has to be 0. Well, it is in fact a common construction. Like if you have some map from somewhere to somewhere, you can take the push out, and if above you have long exact sequence, you will get long exact sequence here, and it's enough to prove for short exact sequences. I think that we can leave it as an exercise. So this map is of course f plus g. Yes. So it remains to change in some way x plus x by x, and to do this we simply take delta I need some space. Well, let's push out the side. We take delta here, yes. This part commutes. We leave this part without changes. And only this guy we change by some be T0, L0. Simply taking pullback. And it is dual to this construction to check that we have long exact sequence here. Well, we also need to what do we also need? We also need a map from, like we still have maps from pi to these members starting from 1, and we need a map from p0 to l0, in fact. But this map can be constructed using pullback property, pullback nearest property, because we have a map from here to here, and we have a map from here to here, such that when we compose with this and this, we get the same thing. So there is a map from here to here, such that this composition is this one, and this composition is this one. This one, yes, and one can check that using universal properties of pullback that this defines a commutative diagram. So, in fact, to construct the long exact sequence that corresponds to the sum of the elements of X, we need to take the direct sum of two long exact sequences. Then on one end we apply the push-out construction with the codiagonal map, and on the other end we apply the pullback construction using the diagonal map and get the required an extension of x by y. And if n more equal than 2, then it's obvious that these two operations commute. Like you can take the pullback, then push out, or push out and then pull back, and we will get the same thing. If n equals 1, then it can be proved too, but it's clear because, in fact, we could, in this construction, we could make first pull back, then push out. Yes, and we still would have an extension and a map from there to there that makes everything commute and ends with f plus g. So we will get equivalent extensions, and for n equals 1, this means that they are isomorphic. And also, one can see that since we make two operations, this pull back and push out, this construction is self-dual. So if we will consider injective resolution and make the same construction, we'll have objective to construct a long exact sequence that corresponds to the sum of maps from X to like Qn, where Qn is the nth member of injective resolution for Y. Then we can apply the same construction and get what we need. Yes. Yes, because there we will have a map from X plus X to Qn, which sends like X Y to f of X plus G of Y, and when we compose with delta, we get a map f plus G. So if we will write down the same construction for injective resolutions, we will get the same thing, and so the bijection yes, this by definition is Rn home Y X. This bijection is a group isomorphism. And the map that we have defined on the extensions some operation that we have just defined on X in the sense of low-exact sequences is called Bayer sum. So in fact, this isomorphism is an isomorphism of abelian groups, where here we have the usual structure of abelian group, and here we have some operation that is induced by the Bayer sum on the equivalence classes. And here again we have a group isomorphism. While like a priori it is not obvious that this operation, when we induce it on the equivalence class, give a structure of abelian group, because initially of course it doesn't give. But this follows from this isomorphism. So we have shown that X is symmetric. Well, some short note on X1. And splitness. Well, let me have an extension of X by Y. So an extension is the same thing as one extension, yes? Then it is called split. Like if it is a part of direct sum diagram, in the sense that what is the better way to define? Like if there exists isomorphism phi from Y to X plus Y, let it be phi and psi, such that Y here by 1, here iota 2, I commutes. Well, it is equivalent to say that there is splitting monomorphism from X to Y, or if it is the same thing as say that there is a splitting epimorphism from E to Y. All of this is equivalent.
I think there are two maps called phi, which is different. From
and yeah, I understand. Let be alpha and beta. So now if you have two extensions of y by x, then the equivalent in the sense in the sense of this equivalence relation, yes. If there exists phi from E1 to E2 isomorphism such that y 1 x commute. Well, why it is so? It is so because what does mean that two extensions are equivalent? This means that they can be connected by a sequence of elementary equivalence, yes. But elementary equivalence, if you have elementary equivalence like let be T1 x, y, T2 x, then you have here equality, and you have some map here, and this map is isomorphism by in fact by 5 lemma, but like you can prove it. You can prove it directly from this diagram. Yes, you take something here, then how difficult. Then you go here, and so you have an element here such that this composition is the same. Like if you have x here, then let it be gamma, yes. Then there is y here such that gamma of y and x give the same thing here. But in this case, we have some preimage of x minus gamma of y here, and it goes in such a way to x minus gamma of y, and we can add the image of it to y and get an element that goes to x, something like this. And in the same way, you can prove that this map is injective, because if something goes to 0 here, then this means that it goes to 0 here, so it has a preimage here that goes to 0 here, and since this one is monomorphism, then this preimage is 0 and an element is 0.
Sorry, this notion of equivalence is not the definition.
Hmm?
This notion of equivalence is not the definition, right? It's just, what
The definition of equivalence was that there was a definition of elementary equivalence. This means that you have such map. And two extensions are equivalent if they can be connected by elementary equivalences. Like the equivalence relation is by definition the minimal equivalence relation that such that elementary equivalent extensions are equivalent. So two extensions are equivalent if you can construct a sequence of elementary equivalences from one to another. The problem is that usually when n2 or more, this relation is not symmetric, the relation of elementary equivalence. But here, by 5 lemma, this map is isomorphism. So in fact, this relation is symmetric. So in fact, two extensions are equivalent if there is an isomorphism between middle terms such that all squares commute when you put id and id. And so if two extensions are equivalent, then really there is a map from one to another, and this map is isomorphism. So two extensions are equivalent if and only if they are isomorphic. And thus we have a theorem okay, that was theorem that says that any extension of x by y splits if and only if x between x and y is 0. So, and it's clear what does mean that any extension splits. This means that all extensions are equivalent to the split one, to this extension. And this means that there is only one equivalence class of extension, and this class is 0, so x1 is 0, because x1 is in one-to-one correspondence with equivalence class. And if x1 is 0, this means that all extensions are equivalent, and in particular, all of them are equivalent to this one. And this means that all extensions splits.
Have we discussed how to define equivalence on the extensions of different lengths? The extensions can be different in length. So what?
Now here, extension is of length 3.
Oh.
There is a notion of n extension.
Okay.
So here we end our part about extant or functors and go to the next topic. Sure. The paragraph is group homology. Group cohomology. And it will be a probably big paragraph. So first we start with definition. And interpretations. In small degrees. let I recall that G module is by definition the same thing as ZG module, yes. G is a group. So if G is a group, then we can form the group ring, which is denoted by ZG, and G module is simply module of this ring. There is another definition, like an abelian group on which G acts by additive maps, but let us use only one. Then also let I recall that A is trivial ZG module if GA equals A for any A in A, G in G. And when we will write Z, we simply we always will mean the trivial G module. Then, by definition, if A is G module, then nth homology of G with coefficients in A is it is denoted by Hn of GA, and it is by definition Ext our ZG from Z to A. Sorry, not Ext, Tor. Here, of course, A is the left G module. And nth cohomology of G with coefficients in A is Hn of GA, which is defined as Ext over ZG Z to A. let us denote by J the kernel of the map from the G to Z that sends G to 1 for any G in G. This map is a ring homomorphism, so the kernel is an ideal. So in fact, J is a free abelian group on the set G minus 1, G from G without the unit. This ideal is called augmentation ideal. And by our definition, that is isomorphic to the G factor G. So again, by definition, is 0 of GA is tensor product of Z and A over ZG, and it is the tensor product of ZG factor J and A, which is isomorphic to A factor J. In particular, zero of GZ is always isomorphic to Z. Zero of G is always isomorphic to Z2. Now, yes, So now a factor JA is by definition a factor the submodule generated by GA minus A for G in G, A in A. And this set is denoted by AG, and it is called coinvariance. Coinvariance under the direction of G. So in fact it is maximal quotient of A, which is trivial G module. Now, the zero cohomology of G's coefficients in A is by definition hom over ZG from Z to A. And one can easily see that it is isomorphic to the invariance, etc. The set of A from A such that GA equals A for any G in G. Well, it's clear because to define a map from Z to A, you have to define it on 1, and you have to define it in such a way that you will get a map of G modules, yes, but the G module structure on Z is that G times 1 is equal to 1. So 1 has to go to some A such that GA equals A for any G in G. And here you easily can see that A0 of G Z is Z, of course. And what about A0 of G Z G? Yes. So to talk about this, let us define one more object, norm element of ZG is the element, sorry, I forgot to say, G is a finite group. And the norm element of the G is the element sum of G for all G in G. Yes, and lemma states that G is equal to n Z if G is finite and equals to 0 if G is infinite. Well, it's not very difficult, yes. Because if you have some element from ZGG, then you can write it as AG times G. If AG integers, then you gonna multiply it by H and see that sum AG HG is equal to this one, and this means that that for any G and H from G, like here it is A H minus 1G, yes, is equal to AG. And since G and H are arbitrary, this means that in fact AG equals to A1 for any G and G. And if G is finite, we get some A1 times M. And if G is infinite, then the sum is 0 because all AG have to be equal, but only a finite number of them can be non-zero. So if one of them is non-zero, then all of them are non-zero. But if G is infinite, this means that there are infinitely many non-zero coefficients, which is not possible.
That M means normal element, right?
Yes, normal element. Sorry. So we get that if G is finite, then 0 homology of G with coefficients in ZG is Z. And if G is infinite, then it is 0. On the other hand, we will see later that the high homology of G with coefficients in ZG is 0 if G is finite, but can be non-zero if G is infinite. So now to compute homology and homology of groups, we need some projective resolution by our definition. And there is one specific resolution which is used in many, to prove many facts about homology and homology, but in fact it is not used to compute them by some reasons. It's called bar resolution. So here bar resolution of Z. So the numbers of this resolution are bar 0, bar 1, bar 2, so on. And bar n is by definition Zg tensor Zg tensor n times. Here, if I don't write any subscript of tensor product, then tensor product is over Z. If it will be over Zg, then I will write it explicitly. So, in fact, it is free here. Yes, I forgot to say, as Zg module, it has a left module structure, in the sense that when you multiply by G, you multiply this copy by, if you multiply by some elements of Zg, you simply multiply this copy of Zg by this element. So, well, I think that as we have considered left modules and their homology, then it's better to write in this way. Yes. So it will be right module resolution. So when we will multiply by some element of Zg, we will multiply on the right, and we will multiply only this copy. And in this way, this guy is a free Zg module with the basis G1 tensor, G2 tensor, so on, tensor Gn for all n tuples Gn, G1, Gn from G.
Is there like a tensor 1? Then like this
What?
thing has n things n G1 through the Gn, and we have like n plus 1 product there. What I have there is Z of G n times and times Z of G one more time. Yeah.
One more time, yes.
Yeah, and here we have only n things.
Yes.
Like
It is, well, sorry, tensor 1. And for convenience, we will write this guy as G1, so on G. So an element of this is written in a unique way as sum for G1 Gn, G1 Gn, A G1 Gn, where A G1 Gn are elements from that G. So now we need to define differentials, yes. And since the differentials have to be morphisms of the G modules, we need to define them only on the generators. So let's define dm of G1, so on Gn, yes. Gn plus 1. This by definition G1, so on Gn plus 1. Sorry, 1 minute. A little difficult such way. Well, okay, let us write in such way. It will be G2, so on Gn plus 1, plus sum for I from 1 to n minus 1 in the ith power. Here we have G2, G1, so on Gi minus 1. Then we have Gi times Gi plus 1, Gi plus 2, so on Gn plus 1. And plus minus 1 in the n plus 1 power of G1, so on Gn, Gn plus 1. Well, and the first thing that we need to show that is that we already have a projective resolution of that, it is of course projective because all modules are free modules. So we need to prove that it is a resolution. Theorem bar d. Yes, and here we simply have a projection because bar 0 is by definition zg, and we have projection from zg to z, yes, with kernel augmentation ideal. Yes. Hmm? Is a projective resolution of Z. So to prove this, we first need to prove that dn minus 1 dn is 0 for any n from 1. Yes. Well, it is quite technical, but not very difficult. Yes. Like if you will apply dn minus 1 to this expression, all terms you will get 2 times, and each one time with one sign, another time with another sign, and they will cancel. Yes, because for example, if you glue together gi and gi plus 1, then and like gj and gj plus 1, then you can glue first gj and j plus 1, yes, and multiply by minus 1 in the jth power, and then gi and gi plus 1, and multiply by the minus 1 in the ith power. Or you can glue first gi and j plus 1 and multiply by minus 1 in the ith power, and when you will glue g and j plus 1, you will multiply by the power minus 1 in the j minus 1 power, because the number of terms before gj decreases by 1 when you glue gi and j plus 1. And so they will cancel. And you can check that like it is something like typical example of summands. But you can check that all summands will repeat 2 times and cancel one with another. Well, there are some more convenient ways to prove it when you denote this map separately by di and dj, and then you write some commutation formulas, but in fact everything will come to this. So the second thing that we need to prove is that in each term the kernel is the same thing as the image. And to do this, we will apply the following trick. We will construct so-called splitting of this resolution. It is, of course, will not be splitting over ZG, because in this case, all homology and homology would be 0, like starting from first one. So it will be a splitting over Z, because you can see that this guy is a free Z module, yes, and all of them are free Z modules too. So if it is a resolution of Z, resolution means that this sequence, when we put also Z is exact, then bar 0 is the direct sum of Z and the image of D0, yes. Then bar 1 is direct sum of image of D0 and image of D1, and so on. Because always we write like bar 0 is the direct sum of something, and this something is projective, so it becomes direct sum of the previous one too. So to prove that over Z, not over ZG, of course. So to prove that this guy is exact, we need to write these maps, splitting this resolution that over Z. And there is a formula for these maps, which is probably wrong, because you write map S-1 from Z to B0, and the maps Sen from Bn to B bar n to bar n plus 1. So here S-1 of 1 is simply the generator of bar 0, yes, which we denote in this way. And here Sen of, we need to define on the Z basis. So Z basis consists of elements of the form G1, Gn times Gn plus 1. Yes. And we send it to G1, so on, G plus 1. Well, we'll see if I'm wrong or right, because probably I had to put some sign here, like -1 in the nth power and -1th power. Let us see. Well, it's clear that pi S-1 is ID, yes. So let's compute S-1 pi plus D0 S0, yes. What's this guy? Not this guy. This guy. Sorry. This guy times G, yes. So when we apply pi, we obtain 1, and when we apply s minus 1, we obtain 1. Yes, it is 1. So now d0 is 0. Yes, when we apply d0, when we apply s0,
When we apply s minus 1, we get this empty bracket.
hmm?
When we apply s minus 1, we get an empty bracket.
Sorry, yes. So it is d0 of g. Well, okay. So here we have to put minus 1 in the n plus 1th power. Well, in this case, we will get minus here, so here g, and by definition it is this bracket minus where it is. This guy, it is this one minus this guy times g. It is guy times g. So s minus 1 pi plus d0 s0 is a d bar 0. And it is again not very difficult to continue this calculation and prove that s n minus 1 d n minus 1 plus dn Sn is equal to id bar. So we need to take like an element of this form and apply to it this thing, take the make the sum and see that only this guy will survive. Yes. Well, so now using this resolution we will understand what is first homology and cohomology. Well, first homology not exactly, but in some case. So the beginning of our resolution is what? We have G, 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 G. Here G tensor H goes to what? To sorry. H minus GH, yes. And here G tensor H tensor K goes to H tensor K minus GH tensor K plus G tensor HK. So we want to compute H1 of G Z. Yes. When we multiply, so to do this, we need to apply the functor tensor of ZG Z. Yes. And we know that if we multiply ZG by this, we get Z. Yes. So we get a sequence Z. Here ZG. Here ZG tensor ZG. Yes. And this map is what? So it sends G to 1 minus 1 times G, yes. But the structure here is trivial, so it is 0. So this map is 0. So the only question is what this map is. So we take G tensor H, and it goes to H minus GH plus G. So, in fact, we see that H1 of GZ is the free Z module with basis G, factor H minus GH plus G for all GH in G. So the question is, what's this? first of all, there is a map from G to here that sends G to G. Yes. So we need to see that it is a group homomorphism, yes. But if you take JH, then it goes to JH, and let's put here. And now this bar means that we respect this relation, so it is G plus H. Yes. Or G plus the class of G plus the class of H. Well, analogously, one can show that G minus 1 goes to minus G, yes. Because you can see that if you put G equals H equals 1, then you factorize by 1, so 1 is 0 here. And if you write G minus 1 plus G, yes, it is 0, so the class of G minus 1 is equal to minus G. So it is a group homomorphism, and it is not difficult to see that if you take G and H, well, we even don't need to see this, because on the left the group is abelian, so the commutator has to lie in the kernel, yes. So we get some map from G factor G to the G factor G minus JH plus H for JH G that sends the class of G to G bar. Now we have a map from ZG to G factor commutator that sends G to G plus the class of commutator. Yes, because it is simply a free abelian group on generators G, and this group is abelian, so we can make this homomorphism. And it's clear that G minus JH plus H goes to where goes to GH JH minus 1 plus GG. It is GG. Here multiplication. So we get a map from zg factor g minus gh plus h to g factor gg, which is a homomorphism of groups, and that sends g to g. So from this in this formula, it's clear that these maps are mirrorly inverse to each other, and thus we obtain theorem that h1 of gz is isomorphic to the abelianization of G. No. Now let us take the resolution, the beginning of bar resolution, and apply the functor whom our zg dash a, where a is some zg module. Well, so if you have something like home zg x tensor zg a, then it is isomorphic to home over z from x to a, of course. Yes. So in this way we can, and if x is z, then it is a. So in this way we get a here, yes. So here we get home over z from zg to a, and here we have home over z from zg tensor zg to a. So where goes a here? It goes the map phi a from zg to a, defined by the equality phi a of g equals to a minus j. No, minus ag. Yes. And if here we have a map f from, in this way we see that really the kernel of this map is I invariance, yes. Like a lies in the kernel if phi a is 0, phi a is 0 if for any g this guy is 0. So for any g, a equals to ag. So, and if we have some f from zg to a, then it goes to some map. Let us denote phi f from zg tensor zg to a, which is defined in the following way: phi f of g tensor h is equal to f of h minus f of gh plus f of g h. Yes. So the kernel of this map we denote it by Z2 GA. Yes. Then Z2 of GA is the set of functions f from G to A such that f of h f of gh is equal to f of h plus f of g times h, and such functions are called crossed homomorphisms. Such functions are called crossed homomorphism. Or sometimes derivations, and the set of such functions is denoted by der of GA. I'm going to finish. I only finish this part. And such maps phi A crossed, they are of course crossed homomorphism because this sequence is a complex. So the composition is 0. So if you get something here from here, it goes to 0, and this means that it is crossed homomorphism. So it is such crossed homomorphism is called principal, and the set of principal cross homomorphisms is denoted by der G. So we get the theorem that H1 GA is isomorphic to the factor set of cross homomorphism by the set of principal cross homomorphism. Well, so that's all.